Okay, well, we've set it up. We've done the basic calibration on it. Now what we want to do is we want to do a performance verification. And then we want to get some sort of, we want to run some sort of sample that says, oh yeah, that's what we're looking for, okay? So what we're going to do is we're going to look at the force zero. We really want to find out where our zero is coming out. And then we're going to do we're going to put the 50 gram weight up there, and it takes 490 millinewtons to offset 50 grams. So we're going to look at that to see if that span is proper. We're going to look at the height zero, the height with 10 millimeters, and then we're going to do the static compliance, which is the eigen deformation that we did, and we're going to do the dynamic compliance. I should have had two sets of work. Okay, so first thing we're going to do is we're going to check the force zero. Up top, I've just put the platform in that we did with the calibration, and I've got the 50 gram weight beside there. We'll do a separate how-to video on really getting the most of the software as far as just getting around it. Remember, there is in the software quick help, and that's everybody's, it's a tutorial, that is everybody's homework. This is chapter, that section, and then you go back and forth with the arrow key over here. And so right now, let me jump. One more thing is whenever we start running this, we need to tear it. And what we do when we tear it, we weigh the probe. That's what the tearing is. We're weighing the probe. But we got a platform on there. We need to offset the weight of that platform. So we're going to go up all the way. We're going to come back down. Anytime people are nervous about their instrument, they seem to go up halfway. So that comes back at 113,277. I always like to throw out the first one because you don't know if we set the platform on, if you bound anything up or anything. So we're going to go ahead and do that twice more. We'll hold, we're going to come back down. 13,228. Hold, back down. By the way, I put a hold in between so we keep everything consistent. We're not sitting there bumping it. 13,277. Now, the goal here, without a platform, which adds a lot of stuff to the top of this thing that has to lift, it's not supposed to, is to get within 0.1. That's basically what you're looking for. Right now we are half of that, so we're doing pretty darn good. So now that we're here, found my tweezers, what we're going to do is we're going to say, okay, we've carried out the probe. We want to find out what the true zero is. So we're going to zero out the dynamic force. And I actually did this a little bit ago, so I know that the true zero is right around here. So we're going to apply a static force. We're going to go over here and we're going to apply that force. Up top, everything changes. Probe's in one place. We're going to go over here and we're going to hope I don't have the old guy shaking stuff, because I certainly do that most of the time. And we're going to lift this up, and we're going to lift it up to the sample where the sample is, right about there, and we're going to let go. Now what you do, that should hold for just a moment and then drift up, not drift down. Well, you saw that it did that. It held for just a minute, one moment, and then it started drifting up. The true static force on this thing is -3 millinewtons. Yeah, we like to set it from, I think the specs say down to -25, but I could be wrong on that, but I like to set it -3 to -6, mainly for if someone is doing extension or something like that. The thing about this is not linear, and so it's really sensitive, and the nonlinearity, we're talking about very small numbers. They're not numbers that's ever going to affect your anything that you're running. But if you're running really low forces, and you can see, say, a 1 difference between here and then right up here, a little bit higher. So it's nice to have just a little bit offset, so you don't have to go and do a specific calibration if you decide to change your hardware. And you know, PerkinElmer, the products folks always said that, and I'm sure anybody, whether it be PerkinElmer or TA, whenever you change stuff, go ahead and recalibrate. And you certainly should check that. It's the best advice somebody can give you. But right now, you're not calibrating this. You're calibrating that. You're calibrating the analytical train. You're looking at your force. You're looking at your zero. You're looking at your height. You're looking at your compliance. And those translate, way past whatever your existing hardware is. So, at any rate, we have our force 0 is at -3. So let's say that we're going to go ahead, we're going to put our 50-gram weight on top. And we're going to change this to -493 since we were already -3. So it's 490 apart. We want to apply our forces. And now we want to see if it'll still hesitate there. So we're going to come back up about to where the sample is, and we're going to let her go. 490 millinewtons, balancing 50 grams of weight, and it's gradually going up. So I think so I'd say our performance verification as far as our forces that we're applying is looking pretty good. So we're going to go over here, we're going to put our static forces back to 100, and we're going to leave the dynamic off. We're going to take this hardware off. You don't really have to hang on to that. I hung on to it because you've got a little bit of friction pulling that off. I don't like banging it all around. Now, you know what we need to do, because we just did it. We don't have this hardware on. We don't know what the weight of the probe is. We need to compensate for that. So we're going to go back into our tear probe. We're going to go up all the way. And we've seen these where if you go up all the way, that's 10.429. They'll stick at the very top, but it'll work perfectly, meet every spec on Earth when you're down in your operating range. And can you run like that? 10.429, absolutely. But you don't really like running with an instrument that you can tell that there is something in there that's messing with you, and so we like to run it all the way up, see if there's anything up there. Okay, 4503. So we're still right in there. We can do it one more time if we want. I'm sorry, 10503. Same thing. There you go. Okay? So this time we're going to look at our 0. And we did our calibration. That's what we offset with the calibration. So right now, let's see here. get rid of our block temperature. Let's go up here to probe position. So right now we're at 0.001375 millimeters. So it's pretty darn low. And we're going to go ahead and, you know, we're right down there where we ought to be. You're going to set zero up when you do your runs. You're going to look at your height, read your height. So we're right down where we ought to be. What do we care about now is the span, the 10 millimeters. So I'm going to go ahead and just automatically re-zero this thing. Okay? And then I'm going to scoot in here a second, and I'm going to put our 10 millimeter quartz standard up there again. And I'd use my tweezers, except, you know, I really stink with the tweezers. Maybe not so much when I was younger. But we're going to come back down, and we're going to give it a minute. I don't know that I got that right in the center, but let's, we'll see what we get. Right now, probe's reading 2.62. And there's a little delay in there, so we're going to let it go ahead and cycle around and see where we're going to be with it. And we pop back at 10, and we're going a little bit down. The spec on this is 1%. Well, we're stabilizing out down here. This is 9.99, and I think we had 7.9 or 8 or 9.98 or something. So we did pretty good on the 1% spec on the height. And you know, if it's going to come up, we need to know how far it's going to be when we measure the amplitude. So we're going to go up again. We're going to take that. You've had an instrument in here with us. You're going to get an instrument back with the numbers from these specs on your shipping sheet. There's going to be performance verifications, everything goes back, what came in, what goes back. And if it's a new one, you're going to it's going to say the same thing what we're sending to you. Okay, now what we want to do is we want to do static compliance. Static compliance, eigendeformation. So to do that, we're going to go over here to initial state. We're going to put our static force at 100, dynamic force at 0. We're going to apply forces. And we're going to be looking up here at probe position. Right now the probe position is 0.0002. And so then we're going to go up here to 1100. Apply forces. And typically this should be under 0.1. I think is that the spec? I think that's the spec. Let me see here what the spec is. Actually have that here somewhere. I do love watching somebody turn a piece of paper. I'm sorry, it's 0.001 millimeters per full scale. And we are plus or minus 1% of full scale. So we have a pretty good full scale there. So yeah, we're well in that. That's 0.002. So we're well in there. Okay, now here's what we're going to do. We're going to go ahead and do our dynamic compliance. So to do that, and this is, you got your oscillating force. With a perfect machine, it's going to come right back. Zero is going to stay the same. So, or it's not going to move. Let me restate that. That wasn't very accurate what I did. So we're going to put dynamic force 100. We're going to look over here at the amplitude. And typically this is going to be under 2. So we're going to go up to 1,000, under 0.2. No, I'm sorry, under 2. And there's a full scale spec on that too. And we're coming up somewhere around 1.9, something like that. You know, so that's pretty good. We're right there in there, you know, we don't have to go, we're right in the spec. Now the next thing we want to do, this is it, except for checking your temperature. Well, you know, the temperature is pretty simple. You put a sample under there, you put a probe on, you heat it up, you look where it comes off, and you put that in your calibration. So what we want to do now that this instrument looks like it's working, we have a RFE material. PerkinElmer's specification on the RFE material is that you should read from 1 to 2. Let's see here. I think it's 1 to 2 to the 10th. PA. So let's go ahead and let's raise this. Now, excuse me for getting in front of you, but I just can't do this from the side. I'm going to put a RFE material in here. Because we know that for this material, PerkinElmer is recommending 220 static and 200 dynamic. We can apply our force. And that gives us about 11 microns amplitude. That's pretty. Gives you plenty of data points to work with. And I don't know if you can see the screen. The screen's coming back 1.77 to the 10th PA. So it looks good. The instrument looks great. The only other thing to do is just simply do the calibration. And if you have if you have any questions on that, then certainly call. We may do something more on that at some point in time. It's pretty straightforward. I hope that helps. From Thermal Support to you, have a great day.